Now that we're talking about power, let's talk about what power is and what electricity is. This section is all about what electrical power is, how we refer to it, and really specifically how we measure and talk about electricity. That's the subject of this particular video. So I'm going to grab my chair and let's go ahead and get started talking about power. So this section is the learning objective is to understand the basics of electrical power and the terms that we use to talk about electrical power, and we're going to get and dive straight into electricity and what we're talking about. So the first thing we need to understand is alternating a direct current. Now, we talked very briefly back in chapter 1 about the difference between alternating and direct current. So let's first talk about alternating current. Alternating current is what plugs in to our house runs on, what our wall plugs are. It cycles back and forth, and the big thing here is this first bullet. It is the most efficient way to transmit electricity over long distances. If it wasn't, that wouldn't be what we plug in. The power comes in on electrical lines to your house that goes to a transformer, and that transformer changes the voltage down to our household current of 110 volts. That's what comes in an electrical plug on the wall is 110 volts. And the cycles, the way it cycles, it's what's called a 60 hertz frequency. So 60 times a second, the power cycles back and forth on a positive and negative sine wave. So that's what comes in from the wall. AC, alternating current, is what comes in from the wall. Alternating current is what runs our house, but it's not what electrical devices run on. So what electrical devices run on is direct current. It's not as efficient to transmit electricity. That's why it's not our wall plug. But it's very stable. It travels in one direction, and it's what most electrical components need. It does not cycle. DC is direct, level current of some voltage. So how do we get from AC to DC? We have something that transforms, just like the big transformer outside on the telephone pole. The ratio of the voltage to a different voltage level, and it rectifies. A rectifier converts alternating current to direct current. So you have transformer rectifiers all over the place that you guys use. Every single time you plug in a laptop power supply, you're plugging in the AC plug in the wall. This power supply is acting as a transformer to change the voltage from 110 to the output voltage of this device, and it rectifies it from AC to DC. So in the end, what you have here is a DC plug that has a very specific voltage on it. And if I could read, it would say the output voltage on here is 19 volts. So it goes from 110 to 19, and it changes it from AC to DC. And that same thing happens in every single one of your iPhone or Android chargers. Any place you put a power brick in your house, it's changing it from AC to DC. So, wall outlet, AC, alternating current at 60 hertz. It alternates in a sine wave pattern. In our electrical equipment is direct current, and it does not alternate at all. So difference between AC and DC current. Now, there's some terms that we want to talk about when we talk about understanding electricity. And those are volts, amps, and watts. There's another one right here I have whited out because we don't talk about ohms in this class. I don't see any reason to. It's not something we can control, so I just skip it. So volts, amps, and watts, and what are they? And I've got a little analogy I like to use in my class to describe what volts, amps, and watts are. So this is a picture, or supposed to be. It would be a drawing if I was doing it in class, but of a water spigot on the side of your house with two different size of hoses that we could connect to it, with water coming out and filling a pail. Now, the water flows through the hose at some rate determined by how much we turn on this nozzle, right? We turn that on, that spigot on, and it causes the water to flow at some rate or some current through the hose. So the current, the amount we turn it on, is what we would determine as amperage in electricity. It is the flow. Amperage is the flow. And when we think about the flow, we have to think about how much we turn on that knob to determine what the current is that's going through the hose, right? You can have a fire hose, you can have a little tiny tube. If you turn it on real low, then you're not going to get a lot of flow through the tube. Now, the size of the hose gives us the potential of how much water can go through it. If I take a little tiny tube, that like the one connected on the back of my refrigerator that fills the ice bucket in the back, versus a fire hose that's that big, they have totally different potentials to get water through them. Potential is the ability to move that water through, but it doesn't say water's through, right? The hose could be empty. This hose could be empty. If I turn the spigot on all the way down, there's no current going through there. They aren't living up to their potential amount of water that could go through it. The last term, so potential is voltage. Potential is voltage. The voltage of something is the potential to have electricity come through it. It doesn't mean that's how much is going through it. That's how much it could potentially, the size that it could potentially have. So the amperage is how much we turn it on, or the current. The voltage is how big of a hose we have, or the potential. And the total that comes out, the water that fills this bucket, is the wattage. Wattage is total power, and it's determined by how much we open the spigot and the size of hose that we have. So it's amperage times voltage equals wattage, or total power. So that's my analogy to try to kind of put these things together in a little bit of how can I, because we can't see electricity, right? We can't see it, so how do we conceptualize what those things mean? So voltage is the potential of a circuit. It's the size of your water hose that you have connected to your house. Whether it's a huge fire hose, whether it's a little tiny hose, voltage is potential. It doesn't mean anything's happening. It's the size that could happen. Amperage, or amps, is the current that goes across that circuit. So amperage is how much we open up that water spigot. So voltage could be very high, but with very low voltage or very low amperage, there's really no shock. In fact, you may have heard this phrase before. It's not the voltage that kills you, it's the amperage that kills you. It doesn't matter what the potential is if there's no real current going through it. However, the potential could be very low with a very high current, and it could kill you. So wattage is total power. Wattage is total power, or how much water we get in our bucket, and it's determined by volts times amps equals watts. Volts times amps equals watts. So potential times current equals total power. Those terms are really important. This chart that you're looking at behind me, there we go, I'm pointing the right way now, is something you need to have in your notes. Voltage is the potential difference in a circuit, amperage is the electrical current, and wattage is the total power, which is determined by volts times amps. And we'll get more to that as we go. So that's the definition of electrical power. So if I've got an electrical circuit running on the wall, I got a plug and I plug this in. If there was no amperage in it, it wouldn't have enough to power this and get out the total power that we need for our laptop. And by the way, that's why some laptop power supplies don't work on some laptops. Because if the wattage of this one is too low, it means it can't put out the total power that the laptop needs. You guys have laptops that need 90 watt power supplies. It has to be 90 as a minimum. And we have 65 watt ones, which will, if you plugged it in, would charge your battery just fine. But your laptop would run terribly because there's not enough power to run it at the speed that it's supposed to have. And we'll talk more about wattage and the wattage requirements of laptops here in a little bit. So, definitions of power. AC alternating current cycles back and forth at 60 hertz, 60 cycles per second. Our wall outlet is 110 volts. Direct power, which is what most electrical devices need, moves in one solid state direction. And what we use to get from AC to DC is a rectifier changes it from AC to DC, and a transformer changes the voltage from that 110 to whatever DC voltage we need on the devices that we have. Last thing I wanted to point out is what the plugs of this are for. Now, if I look at a plug, there's 3 different things on a normal plug, just like this picture. The one on the bottom is the ground that has no electricity flowing through it whatsoever. It's important to know whether your house has a good ground, because if it doesn't, then this doesn't do anything. And neither does any of our power protecting devices that we're going to talk about later in this chapter. So the ground goes through, and then one side of this is neutral or return, and one side of this is hot, or the one that actually will shock you. So 2 of these plugs, realistically, don't do anything to you. The third one, the hot one, is the one that's traditionally smaller. And that's if you look at different size plugs. And if you look, the one that's smaller, see it on the right, it's pointing to the hot one on the right. The smaller of the plugs that you see on that diagram there is the one that, if your house is wired correctly, the electricity comes through into and then goes out, and you are billed for the flow from hot to neutral, because it's the movement of electricity that powers your devices. It's not like it just comes in and doesn't go out, which is why you get shocked, because if you touch this hot, it's trying to go to ground, and if it can't go through the neutral line, it will go through you. So that's what the different plugs are when we look at our electrical outlets. I just wanted to point that out as well.